All right, question number 2 on APChem quiz number 2 for the third trimester. Now we're looking at the conjugate base of the acid you selected in question number 1. So the acid I selected in question number 1 was nitrous acid, HNO2, and as an acid it looks like this. Now we're going to turn it around, and instead of looking at things from the acid perspective, we're going to look at things from the base perspective. So nitrite is the conjugate base of nitrous acid. Since nitrous acid is a weak acid, its conjugate base is going to be a weak base. So again, this relationship between weak acids and weak bases, very important one to keep in mind and one to recognize. All right, I'm tired of red. Let's go to blue, okay? Formula of my compound, I'm going to select sodium nitrite. That's the sodium salt of nitrous acid. Sodium nitrite, you notice I use the word salt. Salt is just a generic term for ionic compound. Don't be fooled by the language. Okay. Show how this compound dissociates when it dissolves in water. Like any good soluble ionic compound, and we know this is going to be soluble because it contains sodium ion, anything that contains sodium ion completely ionizes, completely dissociates is the appropriate word, when it goes into water. And everybody remembers the reason for that. Water, being a polar molecule, is able to hydrate both the cation and the anion, overcoming the ionic bonds that hold sodium ions and nitrate ions together into the solid state and liberating those. Okay? So again, this is the dissociation. We'd write a similar reaction for the rest of these. I'll do them real quickly. Sodium cyanide dissociates into sodium ions and cyanide ions. Again, be careful with your charges. Remember your polyatomic ions. Sodium fluoride dissociates into sodium ions and fluoride ions. Finally, sodium benzoate dissociates into sodium ions and benzoate ions. Okay, there we go. Notice the similarity in all those reactions. That's what we mean by dissociates when it dissolves in water. Now, sodium ion, spectator, no chemistry there. Always view sodium ion as a spectator. The key to these is the anion. All of these anions, because they are conjugate bases of weak acids, all of these anions, remember anion means negative ion, these anions are all weak bases. So continuing with nitrite, let's change color. Let's do go to green. Nitrite, show it acting as a base. So nitrate ion in aqueous solution is going to find some water molecules to bump into. Being a base, it's going to accept hydrogen ions. When it does that, it's going to form nitrous acid and hydroxide. Bingo. Now, again, this is our Bronsted-Lowry definition. We've got a base as an acid, a proton acceptor, hydrogen ion acceptor, water as a proton donor. Notice that this also satisfies the Arrhenius definition. Arrhenius definition says what? It says that a base is any substance that produces hydroxide ion in solution. So the Arrhenius in aqueous solution. So the Arrhenius definition is focusing on the outcomes of the reaction. The Bronsted-Lowry definition is broader because it's actually talking about what's happening in the reaction. Something is losing protons, that's the acid. Something is gaining protons, that's the base. Okay? So for the rest of these, really similar reaction. Cn minus plus H2O liquid. Again, transferring a hydrogen ion, HCN, aqueous. There's our hydroxide again. So there's cyanide ion acting as a weak base, fluoride ion, similar reaction, fluoride ion, finds a few water molecules. Hydrogen ions get transferred from the water to the weak base, forming hydrofluoric acid, the conjugate acid, and hydroxide. Finally, our benzoate ion. Don't forget that negative charge. Reacts with water. Again, accepting a hydrogen ion to form some benzoic acid. And hydroxide. All right. General reaction here. Yeah, we could represent the base as B minus. These are all anions reacting with water to form the conjugate acid and hydroxide ion. There we go. There's the general form of that reaction. Okay? Conjugate acids, conjugate bases. All right. Again, if we look at that general reaction, here is my base, right? Base, proton acceptor. Here is the conjugate acid. All right. Here is the acid, right? Here is the conjugate base. All right. So there's the general description of acid conjugate base. Notice the base and conjugate acid, acid conjugate bases are on opposite sides of the reaction and only differ by a hydrogen ion. The acid has the hydrogen ion, Hb, the base, B minus, does not. The acid has the hydrogen ion, H2O, the base does not, OH minus. So if we go up here, in our specific reaction, nitrite is the base, nitrous acid is the conjugate acid. Water is the acid, hydroxide is the conjugate base. Go to the next one, just to make sure, critically important that you can look at a reaction and diagram it this way. Here's our base, cyanide is the base, it's the proton acceptor, HCN is the acid. Water is the acid, hydroxide is the conjugate base. Fluoride is the base, it's the hydrogen ion acceptor, HF is the acid. From this perspective, it's the hydrogen ion donor, right? Again, different color, let's be consistent, go to red. Water is the acid, hydroxide, conjugate base. Finally, finish up the series here. Benzoate ion is the acid, it's accepting the proton. Benzoic acid is the conjugate acid. It's going to donate the proton on this side of the reaction. And again, water is the acid, hydroxide is the conjugate base. All right, so for my specific reaction of nitrous acid and nitrate, nitrous acid is the acid, conjugate base is NO2 minus. Water is my acid in this case, OH minus is the base. This demonstrates a couple of nice things. Notice that if you went back and looked at question number 1, water was acting not as the acid, but as the base. In this case, water is acting as the acid. Again, water has this amazing property of being amphoteric. Depending upon who water is up against, okay, water can be both a proton donor, an acid, or a proton acceptor, a base. Okay, so just one of the many versatile properties of water. Probably its most important chemical property is its ability to act as either an acid or a base. Very weak in both cases, but significant. All right, let's write the equilibrium constant expression for the base. Again, if I use the general expression, if I use my general term here, my equilibrium expression is going to look like this. Kb is going to equal the concentration of the acid, Hb, at equilibrium times the concentration of the hydroxide at equilibrium divided by the concentration of the base. Notice we do not include water as part of the equilibrium expression. Okay, water is not included as part of the equilibrium expression. Please do not include it. Very good chance, excellent chance that somewhere in the course of the AP Chem exam, either over the course of the multiple choice or in the free response section, particularly on question 1, remember question 1 on the free response is always an equilibrium question, you are going to be asked something about the equilibrium expression. Real common mistake is to add water in the equilibrium expression. Water does not appear in the equilibrium expression. Please remember that. All right, I want to make sure we get the simple points at least. All right, good, excellent. Now, for our particular reaction, for our specific reaction with nitrite ion, our specific reaction is going to be Kb, is going to be equal to the concentration of the nitrous acid times the hydroxide ion concentration divided by the nitrite concentration, okay? So there's our specific equilibrium expression. You would have specific equilibrium expressions for all of these. Again, water does not appear in the equilibrium expression. All right, good. Scroll down here. Now we want to figure out what the Kb is. Notice we've got the Kas from problem number 1. We've got the pKas. We're interested in the nitrous acid, but we're interested in the conjugate acid. A couple of things to remember. The product of the Ka times the Kb is equal to Kw, which is the water on an autoionization constant, which at 25 degrees, where we'll always be working, is 1.00 times 10 to the minus 14th. So Ka, or Kb, is equal to Kw divided by Ka. This shows the mathematical relationship between an acid and a conjugate base. As the acid gets stronger, the base gets weaker. Kw is a constant. Okay, so as one gets bigger, the other one gets smaller. Well, we know the Ka, so we're just going to plug in here for our particular reaction, 1.00 times 10 to the minus 14th divided by 10 raised to the minus 3.40 power. Again, Ka equals 10 raised to the minus pKa. Just like you would get hydrogen ion from pH, this is how you get Ka from pKa. Okay? If we do that calculation, the Kb for our nitrite ion is going to be a relatively small 6.3 times 10 to the minus 9th. Now this makes sense. Weaker base stronger acid. Notice I'm not saying strong and weak, I'm saying stronger and weaker. So this is all relative. But as the acid member of the conjugate pair is stronger, the base member pair is weaker. All right? Good. All right, so we've got our Kb. Now we're set to come down here and actually use that in a calculation. So, nitrite, we wanted to determine the pH. We know the solution is going to be basic. Therefore, we know that the pH will be greater than 7. Because this is a weak base, though, we're not looking for it to be substantially greater than 7. So we'll be able to check our answer when we're done here. So nitrite, I'm going to ignore the state designations. Everything here is happening in aqueous solution, reacting with water to form nitrous acid and OH minus. Maybe you're sophisticated enough, you might be able to skip the ice table, but it's a very clear way of documenting your work for the AP Chem grader. That's what they're expecting to see. So, my initial conditions, 0 for the 1.10 molar for the nitrite ion concentration, 0 for nitrous acid, 0 for hydroxide. Again, we're assuming that the hydroxide that's produced by the water, 10 to the minus 7th, is insignificant. Change, reaction has to go to the right. equilibrium concentrations. Bingo. Okay. We're now going to take those x's, those equilibrium concentrations, plug those into the equilibrium expression. So x for the concentration of the acid, x for the concentration of hydroxide, 0.10 minus x, and we're going to set that equal to the Kb, which is 6.3 times 10 to the minus 9th. All right. We're going to make a simplifying assumption, again, that x is much, much smaller than 0.10. Probably a pretty good assumption. Kb is small, so we know x is going to be very small. So this simplifies to x squared over 0.10 equals 6.3 times 10 to the minus 9th. And when you solve that, x is equal to 1.6 times 10 to the minus 6. Our assumption is good. Now, a couple of cautions. X is small, okay? But x, remember, is equal to the hydroxide ion concentration. So the hydroxide ion concentration is equal to 1.6 times 10 to the minus 6. We want to know what the hydrogen ion concentration is because we need to get the pH. So a little extra work here. Don't be fooled here at this point. Many people think they're finished when they've gotten x. And remember, we're working from a base perspective. So a couple of ways to do this. We could first come along and say, okay, Kw, the product of the hydrogen ion concentration times the hydroxide ion concentration in any solution has to be equal to 1.0 times 10 to the minus 14th. So therefore, H plus is equal to Kw divided by the OH minus 1.00 times 10 to the minus 14th divided by 1.6 times 10 to the minus 6th. Okay, the hydrogen ion concentration is going to be 6.3 times 10 to the minus 9th molar. Okay, pH is going to be the negative log of that, and the pH is going to work out to be 8.20. Right? Now, another way we could have worked that through. Get a little bit more room here. The other way you could have worked that through, same thing really, but we could also say that we know that pH plus POH equals 14. These two expressions are the same expression. This is the logarithmic form. So I could have calculated my POH. POH is going to be the negative log of the hydroxide ion concentration. So POH is going to be my POH is going to be 5.80, and then I could have figured out that pH is going to be 14.00 minus 5.80, or 8.20. In any event, okay, this is the pH meets our criteria that it's greater than 7, just for reference purposes, as we did in the previous example. Let me get a little bit more space here. If we had had a strong base, let's suppose I had had a strong base. What would a strong base be? How about 10th molar sodium hydroxide? Again, sodium hydroxide would be completely dissociated. Therefore, the hydroxide ion concentration in 10th molar sodium hydroxide would be equal to 0.10 molar. The POH of this solution would be 1. The pH of this solution would be 13. All right, so there sort of is our benchmark, a base where we have the maximum concentration of hydroxide would have a pH of 13. Our pH is only 8.20, so definitely greater than 7, definitely basic, but far, far from what we'd see in the strong case. Okay, hope that illustration makes a little bit of sense. So kind of benchmarks. We know pH has got to be greater than 7, but the pH is not going to be significantly greater than 7 because we're dealing with a relatively weak base. All right, we can demonstrate that here with percent hydrolysis or percent dissociation. Again, one more time, what we're looking at here is what percentage of the nitrite ions actually undergo this reaction? What percentage of nitrite ions associate with water or break up water, hydrolysis or association, to form the nitrous acid and hydroxide? Okay? Again, if we go up here to look at the work we did, just as we talked about in the previous example, X here is a measure of the extent to which the reaction goes to the right-hand side, right? X, we figured out, was 1.6 times 10 to the minus 6. So our percent association, or percent hydrolysis, is just going to be equal to 0, to our concentration of either the hydroxide or the acid, acid produced, 1.6 times 10 to the minus 6, divided by the original concentration that we started with, 0.10, times 100%, and you can see this is going to be a very, very tiny percentage. It's going to be 1.6 times 10, 1.6 times 10 to the minus 5th times 100. This is going to be 1.6 times 10 to the minus 3%, or 0.0016%. Okay, did my right? Okay, everybody good? Tiny, tiny percentage, tiny, tiny percentage. Okay? So if I had 10,000 molecules, okay, or 100,000 molecules, excuse me, only 16 of them would undergo the reaction. All right? So not surprised that this very small percentage is another indication that we have a very weak base. But even though it's a weak base, it's significant enough to change the pH of the solution. So weak does not mean insignificant. I hope that makes a little bit of sense. All right.